Okay, so now that we've talked about the null and alternative hypotheses, type 1 and type 2 errors, as well as statistical significance, we can move into a discussion of our first inferential statistical tool, which is chi-squared. Chi-squared is a tool that allows us to evaluate for any categorical variable pairing, for example, nominal-nominal, nominal-ordinal, ordinal-nominal, to evaluate whether or not it's more likely that a relationship exists in the world or whether or not a relationship does not exist in the world. In other words, chi-squared is going to help us evaluate whether or not the null hypothesis is more likely to be true or the alternative hypothesis is more likely to be true based on the evidence we've collected. So the way a lot of these statistical inferential tools work is we're always going to start with the assumption, just like we do in court, that the null hypothesis is true. We're going to assume that there is no relationship in the world between x and y. And based on that assumption, we basically take a distribution of what the evidence would look like. So if there were no relationship between x and y, what would the distributional evidence look like? Well, we know that if you were really innocent, most of the evidence in the world would basically point to signs that you are innocent. There would be statistical chance, though, that you could observe some evidence that would point to you being guilty. So we're always kind of assuming that. We're assuming that the person is innocent, the null hypothesis is true. Then we're saying, based on this assumption of what the world would look like, how different is the evidence we observe? If the evidence that we observe is very different from our assumption, we might conclude then that the relationship does exist because this information was drawn from a different world.
All right, let's take a look at how we calculate chi-squared to gain an understanding of what the measure is trying to tell us. At its essence, chi-squared is a measure of the difference between what we observe in our crosstab versus what we would expect to see if the null hypothesis were true. So looking at the formula, O is going to refer to the observed frequency, E is going to refer to the expected frequency if the null hypothesis were true, and I refers to each individual cell entry. The formula then is calculated by taking each observed frequency and subtracting the expected frequency, which gives us the difference between our observations and our expectations. We're going to square those differences to get rid of the negative numbers, and then divide by the expected frequency to take into account that tables have different sizes due to n. We're finally going to add all those squared differences that are weighted by the expectations together, and that's going to give us a total number that represents how different our observed table is from our expected table. To help illustrate how this works, let's suppose that we surveyed 100 people. Our independent variable x is gender, which we'll simply code as a dichotomous variable for male or female. Our dependent variable y is party affiliation, and for simplicity's sake, we'll code this as Democrat or Republican. This gives us 4 possible options: male Democrats, male Republicans, female Democrats, and female Republicans. Let's further assume that we have 50 males and 50 females, and 50 Democrats and 50 Republicans, although at this point I won't define how many male Republicans we have, how many female Republicans we have, or how many male Democrats we have, or how many female Democrats we have. Let's start by creating a crosstab that just takes into account this information. As usual, I placed our independent variable, gender, female, male, on the columns, and I placed our dependent variable, party ID, Democrat, Republican, in the rows. I filled in here that we have 50 Democrats, so our Democrat row total is 50. We've got 50 Republicans, so our Republican row total is also 50. We have females of a total of 50, so our column total for females. And we have our column total for males is 50 as well. We add up our column totals, 50 females plus 50 males. That gives us 100 total observations. And we add our row totals, 50 Democrats plus 50 Republicans. That also gives us a total of 100. So our first step in calculating chi-squared is to figure out what the expected observations should be if the null hypothesis is true. That is, if there were no relationship between gender and party ID, how many female Democrats would we expect, how many female Republicans would we expect, how many male Democrats would we expect, and how many male Republicans would we expect. Now in this example, I've kept the math fairly simple, so if we have 50 females, 50 males, 50 Democrats, and 50 Republicans, the expected frequencies for each cell entry would simply be 25. That is, if there is no relationship between gender and party ID, we'd expect that half of the Democrats would be female and half of the Democrats would be male, half of the Republicans would be female and half the Republicans would be male. And likewise, half of the females would be Democrat, half of the females will be Republican, and half of the males would be Democrat, and half of the males would be Republican. In more complex tables, we can always calculate our expected frequency by taking the row marginal total, adding it to the column marginal total, and dividing by the total number of observations. In other words, we would figure out each individual cell entry's expected frequency by taking the total for its row, adding it to its total for its column, and then dividing by n. So for example, the Democrat row total is 50, the female column total is also 50, so we'd figure out the expected frequency for female Democrats by multiplying the Democratic row total, 50, times the female column total, 50. That would give us 2,500, and then dividing by 100. When we do that, we would get our answer of 25. So really, calculating chi-squared is about figuring out how much our observed frequencies differ from our expected frequencies when the null hypothesis is true. That is, what we're really asking is if our observation significantly differs from our expectation, that there is no relationship between, in this case, gender and party ID. Before we actually look at calculating chi-squared, though, let's just assume that our observed frequencies perfectly matched our expected frequencies. That is, if our observed table had 25 female Democrats, 25 female Republicans, 25 male Democrats, and 25 male Republicans, the difference between our observed frequencies and our expected frequencies would be 0. That is, if you subtracted the 25 expected female Democrats from the 25 observed female Democrats, you would get 0. You would get a 0 for subtracting the 25 female Republicans from the 25 observed female Republicans. You'd get 0 from subtracting the 25 male Democrats from the 25 observed male Democrats. And finally, you get 0 from subtracting the 25 expected male Republicans from the 25 observed male Republicans. So, of course, if you plugged in those 0 differences into our chi-squared formula, you would get 0 squared over 25, which is still 0. Add that all together, and you'd have a chi-squared of 0. You can easily imagine that even with some sampling error, we'd probably still conclude that the null hypothesis would be 0 if the observed frequencies did not really differ significantly from the expected frequencies. For instance, if you had, let's say, 27 female Democrats and 23 female Republicans, you might just conclude that, well, it's so close to the expectation that we're not really seeing enough variance to conclude that females are distributed more evenly around one party or another. Alright, so here I've plugged in some made-up data just to illustrate how we calculate chi-squared. So let's suppose that in reality we observe 37 female Democrats, 13 female Republicans, 13 male Democrats, and 37 male Republicans. How would we calculate chi-squared in this instance? Well, what I've done here in the table that you can see above our observed and expected frequency tables is a calculation that I've just done in Excel. So here I've listed each cell entry in our first column, female Democrat, female Republican, male Democrat, male Republican, and as well as the total. We have our observed frequencies for each cell, which come right from our observed frequency table, 37, 13, 13, and 37, and our expected frequencies of 25 for each cell entry. You can see there that both the observed frequency column and the expected frequency column total 100, which represents our total number of observations. Our first step is to calculate what's in the parentheses of our chi-squared formula, so we're going to subtract our expected frequency for each cell entry from its observed frequency. So here, for female Democrats, we have 37 observed and 25 expected. We subtract the 25 expected from the 37 observed, and that gives us a difference of 12. We do the same thing for female Republicans. So here we observe 13 female Republicans. We're going to subtract our expected frequency of 25, and that gives us negative 12. We do the same for male Democrat and male Republican, which gives us negative 12 and 12, respectively. Now you'll notice here that we can't simply add up those differences, because if we add up our differences of 12, negative 12, negative 12, and 12, we get a total difference of 0. This is a common problem that we see in statistics, and a common problem we've seen already in this class. We have to get rid of those negative numbers. And our solution for getting rid of negative numbers most of the time is to square away the negatives. So here we square our 12, we square our negative 12, we square our negative 12, and we square our 12, which gives us 144 for each cell entry. Our next step is to divide our squared differences by the expected frequencies. So here we're going to divide the 144 by each cell's expected frequency, which in this case are all identical at 25, which gives us 5.76 for each cell entry. The reason why we divide by the expected frequency is because tables with different values in it could significantly impact our results. So here we observe a difference of 12 units, so a square difference of 144, out of a total expectation of 25. Now you can imagine that you could have, let's say, an expectation of 250 females, and maybe you observe, let's say, 262 female Democrats. Your difference would still be 12, but 12 out of 25 is a much bigger proportion than 12 out of 250. So we always divide by the expected frequency to account for the fact that there are different values in tables with different n's. So finally, after we've divided by our expected frequencies for each cell entry, we can add up all those cell entries, and that final sum gives us the value of chi-squared, which I've highlighted in yellow at 23.04. Once again, this is just a really simplistic example that uses a symmetrical expected frequency table, but the same rules apply no matter what type table you have or how big your table is. The next question is whether or not that chi-squared value of 23.04 is different enough to reject the expected frequency table and the null hypothesis, which we'll discuss more in our next video.